Okay, hello everybody. I'm Lea Schneider, and I'm going to present today some work that I did as part of my PhD studies that I did with Jan Esper and Jason Smerdon. And I also want to mention Felix Bretis, who is an econometric scientist at Oxford. He also contributed quite a bit. And what I'm going to talk about is a approach to reconstruct large volcanic events based on a summer temperature reconstruction. And what I want to add to this title is that this summer temperature reconstruction is based on tree rings. So I guess many of you heard about this debate about whether or not tree rings are actually able to capture volcanic cooling or not. So there's been a pretty clear answer from the dendro community, I think, and the answer is yes. But what we have to keep in mind is that there are maybe parameters which are better able to represent volcanic cooling than others. And the most abundant parameter, which is tree ring width, is maybe less appropriate than tree ring density. And that's why we clearly focused on tree ring density data in our reconstruction approach. And that is kind of new, so this was the first 1,000-year-long density reconstruction for the Northern Hemisphere. And our initial idea was, of course, to analyze the volcanic cooling, so give some estimate about that. And then we wanted to compare it with the existing archives. So first we looked at the historical observations, and we saw that, yeah, they match, but some of the biggest cooling events that we had, they just didn't, they were not included in the historical observations. And on the other side, we had a lot of cooling events, in the historical observations, there were a lot of big events that we didn't find in the tree ring reconstruction. And this is probably because they were big in size, but probably not so much, there was not so much sulfur in the ash cloud. So then we went to the ice cores because there we should get this sulfur signal much better. And again, we found some quite nice agreements, but also some disagreements for particular eruptions. And that's why we then thought, okay, why not generating an independent record just based on our knowledge from the tree rings. So this was our idea. And first I'm going to show you the reconstruction. So this is extratropical northern hemispheric temperature over the last 1,000 years, and it is a version of the reconstruction which has, as you can see, no low frequency variability, so it was processed in a way that this was not preserved. But what you also see are these large cooling spikes, negative cooling spikes, and our hypothesis was that if these cooling spikes are outside the range of natural variability, then there must be an external driver triggering this cooling. And then we could also only think of volcanic cooling because this is the only that causes such abrupt events. And then the idea was to create a detection algorithm that searches for these volcanic fingerprints, and it's not only designed to detect single years of cooling, but it searches for this specific pattern of an abrupt cooling, and then afterwards a smooth recovery of, in this case, 2 years. But we actually found out that the exact shape doesn't matter all that much, so we can also detect events which differ from this suggested shape. And then running this algorithm on our reconstruction gave us 14 break events, so 14 events in which there was an event detected. And you can see the break magnitude given by these black dots here, and this is a time-integrated estimate of the magnitude of the event. And if we now zoom in on each of those 14 events, this is going to look like this. So we have the break in the central year, and then 3 years prior and 3 years after the event in this figure. And what we wanted to do now, go back to the ice core data and look how they compare. So we used the 3 latest forcing reconstructions from Gao et al., Crowley and Unterman, and from Siegel et al. And we produced, again, these time-integrated estimates so that they all conform to the way that the Siegel et al. Record was produced. And it's also quite useful to have it as such single-year peaks to compare it with our event list. And I just want to quickly show you this example of 1230. So there was initially an ice core event in 1227, put there by Gao et al. And then Crowley and Unterman, they changed this date from 1227 to 1229. And then Siegel et al. Finally put it in the same year as we find it in the ice cores. This is quite a nice progress, I think. And in fact, we found a very similar pattern for the whole list of events. So if we now superimpose all those 14 events, we will find that in the case of Gao et al., there's quite a bit of more spread around this central year than we find here in the Siegel et al. Reconstruction. So the dating definitely improved. I think this was already shown this morning by Matthew Tuhey, but this is sort of a confirmation from the tree rings. One thing I should point on is this event. It's 1695 in the tree ring, in the ice cores, and 1698 in our reconstruction. And then our next idea was that if these 2 parameters, so the ice core sulfur basically, and the cooling estimates, if they are derived from a common source, so from the stratospheric sulfur, then it might be possible to regress the parameters against each other. And that was our next experiment. So we put the radiative forcing derived from the sulfur on the y-axis and our cooling estimates on the x-axis, and we made a simple linear regression. And I know that a linear model is probably not the most appropriate in this case, but it was still useful to show some things. One thing that sticks out is 1258, and this already indicates that a linear model might be not the best choice, because the big eruptions are known to have are expected to cause less cooling. But what I find very interesting about this way of plotting it are the very small events. So we have here some weak forcing events, especially in the Crowley reconstruction. They have almost zero forcing, but still they produced quite some considerable cooling in our reconstruction. And this doesn't really match that well. And I think this is also quite an improvement in the Siegel et al. Reconstruction, because here, also for the smaller events, there's still some forcing there. And this better explains the cooling that we find. But unfortunately, the model fit is becoming worse in the Siegel et al. Record, and this is again probably due to 1258, but then also due to this 1453 eruption, which is somehow not in agreement with the tree rings anymore. Okay, so what this detection approach is also good for is to analyze the volcanic cooling. So we also wanted to generate mean volcanic cooling estimates. And usually this is done by looking at the sulfur records. So here's again the Siegel et al. Events, the 10 strongest events. And then here on the other side, it's our detected events from our approach. And of course, if you use the detected events, this will give you sort of a maximum level. And you can also see that in the superposed epoch analysis. So the green bars referring to our detected events, they cause a much stronger cooling and this is important, also a more abrupt cooling. So the recovery is much faster than if we look at the Siegel et al. Events. And what this approach is really useful for, I think, are the comparisons with the climate model simulations. Because even if you just use a couple of model simulations, they might have different forcings. So it's very difficult to find one common list of volcanic events that you can analyze in these different simulations. And also, you should not really expect the tree rings to respond to every of those forcing events, as I just showed you. So our idea is that we could also use individual lists and estimate the maximum cooling produced by these individual lists in the temperature records. So here I add 5 model simulations from the PMIP3 model runs, and each of those 5 lines has its own set of volcanic eruptions behind. And as you can see, now the cooling spike is much bigger compared to the one in the proxy records. But don't be too much impressed by this. It's also because there's more background high-frequency variability in the models compared to our reconstruction. So this explains some of this difference, but still, even if you consider this, the models are actually showing a stronger volcanic impact. And then what's also very interesting is that the shape of the cooling pattern is a little different. So in the in the model simulations, the second year, so the year after the event, has still 75% or around 70% of the cooling compared to year 0. And in our proxy reconstructions, it's only 50%. So this is something to consider in addition. So to sum this up, I think that this alternative record of volcanism helps us because it gives us somewhat an in-between perspective on volcanism between the proximal historical observations and then the distant deposition records from the ice cores. We could also show that it confirms the improvements in the ice core records, but still there's some particular disagreement in the 1450s and 1690s. Yeah, and I think it has implications for volcanic cooling estimates when we compare proxy reconstructions and model simulations. So, yeah, this was the work from my PhD, and I hope that I can somehow continue this in my future position because, yeah, there would be some more work to be done. Yeah, thanks.
I was a little confused by how you define year 0. Was it the year of the eruption or the year of the maximum cooling? Because for tropical eruptions, they should be off by a year, but for high latitude, they should probably be the same.
Yeah. So in our case, the cooling is the year 0, but you're true. So if we look at the historical records, it's sometimes 1 year off. So there's some lag. And I'm actually surprised that the match with the with the ice core forcing reconstructions is so good because they should somehow already consider this lag, but they are mostly in year 0. So yeah. But I should probably also say that the Siegel et al. Record at that time was not produced with the atmospheric dispersion model for the aerosols. So this is just based on the ice core sulfur increase, I think. So the dates might change a bit if we use the actual evolve 2K thing. I think they improve.
Did you also find some false positive, like low density linked to no eruption or something like that?
Mm-hmm. Yeah, there actually our very smallest event that we found, it was 1099. We could also only match it with the spike in the Crowley record, so the confirmation there is a bit weak. I'm not 100% sure that it's an eruption. And then we also searched for positive events, but we reduced our threshold though, so that the positive events are excluded. So the positive events were usually smaller than the negative ones. So by doing that, I think we lost most of the false positives, and I'm quite confident that the remaining ones are volcanoes.
Where are the tree records from?
It's a Northern Hemispheric compilation of 15 MXD density chronologies.
All right, okay, so thank you, and thanks everyone for being here at this Joint Fix Climate History Network session. So our title here, or my title, is Volcanic Eruptions as Historical Actors in Chinese Dynastic Collapse, and this is the work of a team led by Chao Chao Gao and I, but if anything doesn't make sense today, obviously you can blame me, which is only fair. Okay, so one of the main framings for VIX is in its examination of social vulnerability and response is to treat volcanic climate shocks as revelatory crises, this sort of concept from anthropology. And this basically follows the thinking that stresses prompt a society to react in ways that can reveal otherwise hidden aspects of those societies, including hidden fault lines, latent tensions and vulnerabilities, and so on. And one of the reasons why volcanic eruptions are so useful in this respect is not only their potentially immediate physical impacts, like we have here the particular depiction of Vesuvius, 1631 eruption, but also their far-flung climate impacts, which can be potentially regional to hemispheric and global. They're very generally impactful on society because they can be multi-seasonal, multi-year, and affect both temperature and precipitation and other environmental variables as well. So they would have posed historical and probably contemporary society quite a challenge. We now also have an ice core-based record of explosive eruptions, explosive volcanism that's sufficiently chronologically accurate and precise to examine fine-scale societal responses. So that's great. And this record obviously comes from the Siegel et al. 2015 paper, just a section of which I've plotted out here, and which has been mentioned probably at least 5 times already today, so I'm just going to basically skip over it. I won't treat it in detail. But this is the record we're using in the rest of the paper in terms of our volcanic dates and forcing magnitudes. So we were drawn to studying Chinese dynastic collapse. We experimented with so many ways to try and present these collapse dates and their durations. This is just one experiment. We were drawn to studying Chinese dynastic collapse in the past 2,000 years because there are quite many of them, 68, and they are very precisely dated. This is largely because each successive dynasty saw itself in the main as the legitimate successor to its predecessors, and as part of that also felt it had, and its historians, its royal historians, official historians, had a duty to detail the history of their immediate predecessors in the knowledge that as their own dynasty eventually fell, be it after a decade or 289 years, their own successor historians would be writing their history. So these collapses can range from quite devastating transitions between ruling families after multiple years and decades of warfare, or under external influence, as when the Mongols invaded China under the leadership of Genghis Khan and founded the Yuan dynasty in 1279, and sometimes resulted in the splitting of the territory, which would have shifted through time as well into multiple rival kingdoms, as in the period of the 5 dynasties and 10 kingdoms, which is pretty self-explanatory, I would hope, between 907 and 960. So this graph is just to give you a quick idea of the number of these dynasties we have in the past 2,000 years, and the range of years over which they reigned. Okay. Of course, now we're not the first to examine various environmental and climatic influences on ancient and medieval China, including the influences of specific volcanic eruptions, and certainly work has shown that Chinese agriculture was vulnerable in particular ways to climatic perturbations associated with eruptions. But what we're doing now, however, is to examine whether there's any systematic association between collapses and explosive volcanism over the past 2,000 years, or, well, the first 2 millennia of the Common Era. So here's one way to begin looking at this. The red bars in this figure show the frequency of volcanic events from the Siegel et al. Record, with ice core-based estimates of the Greenland sulfate deposition. And we've split it into 4 panels over the past 2,000 years. So even when we exclude very small events in the record with less than 5 kilogram per kilometre square deposition estimate, we're still left with 156 events now in the Siegel et al. Record, which is many more than previous records had. And these events are potentially capable of impacting climate and hence potentially contributing to the collapse of dynasties or contributing to stress, climatic stress on dynasties. So the grey bars, by the way, starting from 850 AD, just show the frequency of warfare through this time for when we have actual warfare data. So we're going to come back to that in a moment. You can ignore it for now. So next we can add in the dates of our 68 collapses in these blue X's. And we can see that some periods are much more stable and unstable than others, of course. One elementary point, but very important to make here, is that it's clear there can be many, even very big, eruptions with no corresponding collapse, including events known to have impacted Chinese climate and agriculture. So this should immediately really warn us against any environmentally deterministic interpretation of whatever statistical associations we might find between eruptions and collapses. There are obviously going to be many other factors important in determining how resilient a society is and how resilient a given dynasty is to volcanically induced climate shock. Okay. I don't have time to, you could have an entire lecture on this, don't have time to cover the many mechanisms that really evolved in Chinese society and governance to mitigate the impacts of climate variations. But they include things like state-level mechanisms in the form of emergency granaries and market interventions, down to a more individual-level food manuals specifying wild plants safe to eat during times of famine. And this one is a depiction from one of the earliest known manuals written by a Ming Dynasty prince in 1406, the Famine Relief Herbal. So returning to this figure, if we were just to count the number of collapses that closely followed an eruption, we would see the following. Here we've just circled in red any collapse that followed a volcanic event within a decade. And if you do that, you see that 60 of 68 collapses follow an eruption within that sort of window, within that time frame. That seems like quite a high amount, but it's not actually a very useful metric. This is mainly because there are now so many potentially climatically effective eruptions that you would expect a high degree of temporal association just purely by chance. So we need another way of looking at this association. So one way of doing this is just to conduct a straightforward superposed epoch analysis. We've seen different styles of these superposed epoch analysis in many of the presentations before me. In this one, we just plot out the average number of eruptions occurring in the 10 years before collapse, shown here in the central window highlighted in grey. So we take this window, approximate and including the dates of collapse, plot out the average number of eruptions occurring in that window, also allowing for a small plus minus 2 year uncertainty, conservative uncertainty in the eruption date from the ice core. And we can similarly plot out the number of eruptions in each of 8 blocks of the same length in preceding the collapses and following the collapses. And so what we can see when we do that very clearly is that the largest value, the largest number of eruptions occurs in the central window proximate to these collapse dates, within a decade of these collapse dates, effectively. And we can assess the likelihood of this value being observed purely by chance, just using a Monte Carlo approach, in which the volcanic event dates are randomized and their correspondence to collapse counted in each of 100,000 iterations or something like that. I think it was 100,000 for this. And what we see is that the number of eruptions observed in our central window here, occurring within a decade of collapse, occurred on less than 1% of occasions in our randomized, randomly generated distribution. Okay. So this result does suggest that there is a systematic association between collapses and eruptions occurring, at least in the preceding decade, over about the 2 millennia of the Common Era. Of course, it doesn't tell us about the mechanisms involved. It might imply things. It doesn't tell us about them really, and how they may have changed through time as Chinese society changed, as its vulnerabilities changed, agricultural systems evolved. But it's still a useful result. And for historians, it now sort of legitimizes the approach to go and look at case studies of specific collapses and specific volcanism. Or spurs us on, or spurs me on at least. Okay, so let's just see. It seems to have frozen here. Okay, cool. Right, so we can start in the remaining time, which is not much, I guess. How much? 2? Woo, okay, we can start to look at how the association might operate. This statistical association might operate by drawing in other data. One of the most readily available societal data sets relates to the level of annual warfare occurring across China between 850 and 1911, including warfare between dynasties and external peoples such as pastoralists in the northern steppe regions and between rival dynasties at times. So we can begin just by running again a superposed epoch analysis, but this time using an annual timescale. 4 warfare levels relative to collapse dates, running out to 20 years before the collapse dates and 20 years following the collapse dates, with year 0 representing the warfare in the collapse date, obviously. I've just highlighted here any years that breach the upper 95% significance bound. Warfare obviously peaks in the years of collapse, but also peaking in some other years. Some of this you would expect randomly, but you see that the peaks, these secondary peaks or other peaks, are occurring particularly in preceding years, as well as a generally above average level of warfare running up to the collapses, and a sort of return to variation around the average after collapses, quite soon after collapses. So collapses are associated with elevated warfare. It's nice to be able to show it numerically like this, but no historian is going to be surprised at that result. Collapse will often result from warfare, and collapse then itself can potentially engender further conflict. So let's bring volcanic eruptions back into the story now quickly. If we rerun the analysis looking only at collapses that experienced a low volcanic forcing, this is what we would see. And now by low, I mean the number of eruptions occurring in the preceding decade was below the median number. And I take this approach simply because there's so many eruptions occurred in this period that very few dynasties experienced no potential volcanic climatic influence in the decade preceding their collapse. So we just take the median, anything below the median in terms of number of eruptions. That's what we see. So here again, I've just highlighted any years that breach the upper 95% threshold or beyond. And what this exercise basically emphasizes is that the level of warfare preceding collapse often is more elevated than in the collapse year itself in these cases. And again, this makes some historical sense because we know collapse was often the result of prolonged warfare. So, also interestingly, it's quite interesting is the quite rapid recovery and drop in warfare after a collapse when a new dynasty takes charge. So, nearly done. Lastly, let's look at the case of collapses under a high potential volcanic influence. You see quite a different picture here. What is most emphasized in this exercise is the high levels of warfare in collapse years with interestingly high warfare levels sustained out to year +1 and +2 before a drop then towards mean levels again. Now, if we look at the two scenarios in comparison, the difference is clearer, probably. The simplest interpretation of this, at least to my mind, is that collapses associated with greater volcanic forcing are not on average a product of preceding societal instability, at least as measured by prolonged or elevated warfare. There may be other types of instability that we're not capturing here, and that volcanism acts instead as a stochastic actor or influence on the probability of collapses, associated with an abrupt but shorter-lived increase in warfare. So the underlying dynamics, the implication is, are likely to be quite different in both cases, and something worth further pursuing. So just basically to finish, in either scenario, one of the most interesting aspects which I mentioned in passing was a quite rapid return to normal levels of warfare. This gives quite an interesting perspective on collapse, which has historically been treated as a sort of a failure of a society of sorts, but which can arguably be seen as an adaptation to instability, whether environmentally related or otherwise. And this effectively parallels arguments made by Harvey Weiss and Ray Baddeley in their 2001 science paper here. And in the context of Chinese dynastic collapse, links, I think, to the influential concept of the mandate of heaven. So this provided the conceptual framework that allowed for continuity between dynasties, in which a new ruling family didn't always work in practice, but most of the time, in which a new ruling family that seized power must only have been able to do so because they'd been given a divine mandate to rule that had been lost by the former dynasty. And Jonathan Fenby, who authored the book here, makes effectively this point, that the widespread acceptance of this concept of the mandate of heaven, he feels, helps society to stabilize quickly after a collapse by helping to ensure the quick acceptance of the authority of a new dynasty. Okay. So that's just really me repeating myself. Since I run over time, I will stop now and say thank you.
The Chinese have pretty good agricultural records.
Yeah.
How do the agricultural records jive with the volcanic records?
We're still looking into that, but I mean, we've got series of rice prices that Chow Chow has looked at, and you can see after some major volcanic events that they do spike. So rice does become more relatively unaffordable, and that certainly would be a societal stress that you could plug into basically the sort of hidden causal links between this association. Yeah.
Okay. Hello everyone. So I will focus my talk on the local impact of the 1257 eruption of Samalas volcano in Indonesia. So only a few slides for the background, which is already known by almost everybody now. So we already talked about this big bipolar sulfate peak that we found both in ice core and in Antarctica for a long time ago. And the summer cooling has been well detailed for 1258 and 1259 by a multi-proxy record. You can have much more details in this nice paper, a very recent paper, and also I suggest to have a look at the related poster if Sebastian has time to print it. So I will focus on the very local impacts of this volcano. As I told you, it is located in Lombok Island, the island next to Bali, which is much more famous. This is a nice volcano, very nice volcano, with a nice crater lake, very big crater lake. The diameter of the caldera is 6 kilometers. And there is a new volcano, a more recent volcano here in the caldera. So what is interesting is that there are several local legends or written or kind of how to say, eyewitness accounts. Is it a legend or other legends or eyewitness accounts? We don't know exactly. This is written in Old Javanese on palm leaves, lontar. This is what we call lontar. And some of them describe the impact of this catastrophic eruption. So we will use that for this presentation. I will try to bridge the written sources and the geology and the geomorphology. So it's a combination of all this, mixed of volcanology, geomorphology, social science, including archaeology, and so on. So a very ambitious project and still ongoing, of course. So to present the result, what I try to do is to put to catch some sentences of the Babad and to compare with the scientific or the geological observation. So what is interesting is that there are some precise words like pumice. Pumice is written in the Babad, and pumice is a proof, if you find pumice on a volcano, it's a proof that a very large eruption occurred in the past. A small eruption cannot do pumice. So pumice and sand fell in the middle of the land, so it refers to the Kleeman airfall units that we found, 3 main units. Very easy to see in the field because of the color, it is white. And another interesting sentence is the rain and fire fell in the ground and burned Talkuwang. Talkuwang is a city, the present name is Taliwang, in Sumbawa, the next island. It's about 50 kilometers away from the volcano. And this is when we draw the isopath maps of this eruption. Yeah, of course, Taliwang has about 5 centimeters of pumice. One of the most important sentences we found in one of the Babad Lombok, is this one, Mount Rinjani avalanche and Mount Samalas collapse. This was very important because the name Samalas comes from this Babad. It's a Sasak name. Sasak is the local tribe, local people. And also Mount Rinjani avalanche, and as you can see on this reconstruction, there is a sector collapse that should have occurred at the same time, just after the formation of the caldera, kind of a big debris avalanche occurred from Rinjani. So another sentence, large flows of debris accompanied by the noise coming from boulders. So maybe it refers to what we call PDCs, pyroclastic density currents, or pyroclastic flows, or New Erton. There are a lot of names. It's almost similar. So the reconstruction of this eruption showed that more than 40 cubic kilometers of pyroclastic material were emplaced. And for the PDC, this is the distribution of the PDC's deposit. The total volume is up to 16 cubic kilometers, with, as you can see, very thick deposits up to 50 meters. I found one more recent, up to 60 meters, and so on. So it's quite difficult to work there, however, because of the extensive mining activities. Sometimes we miss some deposits, natural deposit, because of that. I want to show you just an example. You can see a nice temple here in the middle of the rice field, but in a strange position. And it's not a valley, actually. The former landscape was like this. It was totally flat, and then people removed all the material, but they wanted to save the temple. So the first, without the temple, we should have missed all the deposit, the former deposits, so we would have made some mistakes for the volume estimation. So another interesting thing is there was no sea between Selaparang and Taliwang. That means between Lombok and Sumbawa. So no sea. There's a strait here, the Ala Strait. So my interpretation is that the strait was totally covered by pumice. And as you can see in this figure, the pyroclastic flows, the PDCs cross the strait up to reach the Sumbawa. There was some observation like that for Krakatau, up to 40 kilometers from the crater. Here it's 60 kilometers, it's bigger, but the eruption itself was much bigger than the Krakatau one. Another thing, also coming from Babad Lombok, the whole country was already inundated by the sea. So is it PDC triggered tsunami? We found a nice deposit in Sumbawa, in the same place here, same area. We'll still need some dating, but at least we have some dating which correspond exactly to the 13th century, mid-13th century. Big boulders, big earthquakes, of course, boulder flows, people escaped and some of them climbed the hills. I think it refers to volcanic debris flows or hyperconcentrated flow, lahar type, because it's not pure lahar in terms of sediment concentration. Anyway, it doesn't matter. So you can see these removed deposits, these reworked deposit, horizontals. This is the ashfall deposit, the pumice fall deposit, which follow the former topography. And this is my PhD student for scale. So this flood destroyed the seat of the kingdom Pamatan. All houses were destroyed and swept away, floating on the sea. This was the second main important sentence, of course, because it reveals the name of the former capital of the kingdom, which was totally unknown. What is still unknown is the location, of course. So we are trying to find it, but it's a bit difficult. We can use the place names. There's in Mataram, Mataram is the main city in Lombok. There is a place called Pamotan. Yeah, it's a bit similar. In this area, there's a big temple, but more recent, dated 16th century, if I'm not wrong. But maybe the former Pamatan was below. I don't know, and it is difficult to ask permission to dig in this kind of sacred areas. We were looking for archaeological remains. Some of them were already found in some very limited places and exposed in the Museum of Mataram, like this one. This comes from Laos or Vietnam, I heard, but I'm not a specialist on ceramic and the local people as well. What we found by ourselves are many things, swords, bricks like this, rings, below the pumice deposits. So we are sure that this was the civilization living before the eruption, before the mid-13th century. We also found interesting walls, kind of this one, it's like a house. There were maybe tens of structures like this, but I'm not an archaeologist, and I will work with a local archaeologist because there are many things to discover. But the problem is that it looks quite old, and maybe it's much older than the Hindu civilization just before the eruption. But I don't know, it's still in progress. So what we try to do now extensively, we try to reconstruct the pre-eruptive landscape of Lombok in order to help the local archaeologists to find Pamatan or other settlements. So what we do, for example, is we use wells and cores. All these were wells that we have the stratigraphy. We are working with the local people. It's a kind we could call that participating stratigraphy. It's not very. Maybe the geologist will be a bit how to say. Yeah, it's not pure science, but the local people know very well the stratigraphy because they dig the wells by themselves. And they know exactly the type of material and also the depth of the layers, and the local knowledge is very strong. So it helps to have a lot of wells, and we also do some course by ourselves in order to check this. So this is a kind of result. Anyway, what is important is when we found some pumice, we are doing some chemical analysis to be sure that the pumice correspond to this eruption and not for former eruption, because other pumice can be found in Lombok. We used also geophysics, for example, to reconstruct the former the paleo valleys here. And then the last, maybe the main result to know is that we reconstructed the former coastal, the former coast, and there was an accelerated coastal degradation since this eruption, up to 3 kilometers, but it's still ongoing. So how do we do to reconstruct this evolution? We are just looking for the pumice. If there are some pumice in the deposit, within the deposit, it means that the deposit emplaced after the eruption. And if there is nothing at all, it was before the eruption. So, and the last one, surprisingly, there are no coral reef in some areas, and if you compare with the pyroclastic, the PDC distribution, it's in the same area. That means that the former coral reef before the eruption are now inland. For example, in Mataram, we can find the former coral reef in the city, in the middle of the city. So, conclusion, I think, I already knew that I have no time, so thank you for your attention. I expected to have no time.
Why was Samalas a mystery until 2013? Like, why wasn't this known for decades?
I always hear the same question, and I have no answer. I don't know why. You mean why nobody found this eruption before? Or?
Yeah, I mean, why? Obviously, locally, it has had an enormous effect on the landscape and in the histories, so why was it? Why was there a mystery about what happened in 1257, 1258, for so long? I mean, people have been asking. I mean, for 20 years, people have been saying, "Oh, the mysterious 1258 eruption." Why was it mysterious for so long?
Yeah, in fact, this eruption was the caldera was known. There was some datings, former dating of the caldera, but the dating were quite old. There was no accurate dating of this eruption. There was a study, an abstract at least, from a Japanese team who identified that the caldera occurred during the 13th century, and that's all. And the Babad Lombot, all the Babads were not known by anybody because it's in the local language. There is a traduction, a translation of this, but only in the summary in Indonesian. And the Indonesian translation is quite general, and it refers to an eruption of Rinjani volcano, not Samalas, Rinjani volcano, which occurred in the past, so nobody cares. So we translated the word Babad, and then this revealed the name Samalas and all the details, the tsunami, the Pamis, and so on. So that's why.
Yeah, thank you for the presentation, for the possibility to speak here. And my paper connects directly to the presentation of Franck Lavigne, because the 57 eruption of the Samalas and its impact on global climate has been discussed intensively by scientists since the source of the so-called mystery eruption was discovered in 2013, well, by him. And then a recent paper, here we have it, has made by Sébastien Gouillet and others, has made an impressive contribution to the scientific and historical information on this event. A detailed case study on its socio-economic consequences is still missing, however, and this paper, my paper, aims to promote a more detailed discussion of the second half of the 1250s in Europe and mainly in Italy. So the year 1258, that's from Sebastian's paper, certainly stands out, but to some, and here I disagree with Sebastian, there's a story before the 1257 eruption and its impact. To summarize my evaluation of narrative sources, in the year 1255, the year 1255 was already characterized in England, France, Italy, and Central Europe by flooding, abnormally cold temperatures, and rain. In 56, we hear of severe thunderstorms and hail across the empire, while the winter of 56 and 57 was reported to be particularly cold all over Europe. The river Thames froze, and France, the Empire, and Tuscany were afflicted by dearth and famine. Now, English chronicles confirm continuous rain and floodings from August 56 to February 57, and the first month of the year were chilly on the continent, while the summer saw a lot of precipitation. Grapes froze in autumn in France. In the same period, there were floods in Bohemia and Britain, and extreme food shortages are reported for England. Monasteries bought grain to sow their fields, processions, illnesses, and an ubiquitous thick fog are reported. All this happened before the dust veil of the Semalis eruption reached Europe in 1258. If we leave these chronicles aside and examine other sources, we find further confirmation. Charters from Germany state that 1257 was a year of failed harvests and odd meteorological conditions. Especially a failing grape harvest in April 1257 is very unusual. We would expect it in October and certainly not in spring. Maybe, and even if it refers to 56, the message is more or less the same. Another indicator are mentions of bridges, bridge repairs or reconstructions, normally quite rare in the 13th century. So we find a concentration of these events in 1257 to 59 all over Central Europe. In many cases, this is the first time a bridge is mentioned at all, but the charters speak of reconstructions, not the exact dates of destruction. So there remains some uncertainty. But I should mention that we have almost no reliable narrative sources for Central Europe east of the Rhine for the possible 58 impact, with the exception of Bohemia. And I think we can further reinforce the idea that administrative and legal texts provide a more detailed picture than narrative sources. If we look at Italian chronicles, which mention the well-known extraordinary precipitation in 1258 and subsequent dearth, so far no surprise. But if we look at the preceding years, as well, for example, at the Bicerna registers from Siena, which reflect the city's income and spending for the years 57 to 59. 56 is unluckily missing. So you have here overall sums, but they are no indicator for harvests at all. Too many other factors are involved. But we do have specific numbers for grain imports. We find large sums spent for grain in 1257, less in 1258, and nothing at all in the first half of 59. Additionally, we can reconstruct the money spent for messengers and know hence about their tasks. From 1259 onwards, we see an explosion of activity when Siena tried to buy grain over large distances from southern Italy. But the messengers and merchants sent to King Manfred's court in Sicily had no success over many months. Since 1257, the powerful republics of Genova and Venice possessed the exclusive rights to buy grain from Apulia. And only after 1259, Siena reached the status of an ally of King Manfred, and in the autumn of the same year, the messengers from Siena finally succeeded and got their grain. Furthermore, the accounts for 1254-55 paint a detailed picture of communal grain management under typical conditions, which were characterized by searching the city's hinterland for grain in spring and early summer. But the second half of 1258 was different. The city's messengers checked, as usual, in August the imminent harvest, but already from September 58, when the 4 months of rain only started, grain imports from Pisa were being prepared. The thorough searching for grain and flour in the mills of the city's hinterland was already underway in November and December. At the same time, substantial alms were being provided for the poor. In the spring of 59, the desperate struggles to import grain from southern Italy set in, as I have outlined above. In 1259, we find for the first time, as a second case study then now, in 1259, we find for the first time in the history of Bologna written statutes, a normative source regulating all aspects of life in medieval Italian cities. I have listed here the ones relevant for our topic. They emphasize food security for the citizens of Bologna and at the expense of social minorities and farmers in the hinterland. The interpretation of the statutes as a result of the food scarcity is plausible if we go back only a few years. In 1256, a good harvest enabled the city to accept migrants from Tuscany, which was already under pressure of famine. Bologna's farmers and traders made a fortune selling grain at a very high price to Florence. Politically, Bologna extended its rule over Forli and Faenza with the explicit aim of securing grain-producing areas for the city. From 1257, we only know of a conflict with Cuneo because this city in Piedmont blocked Bolognese grain imports over the River Po. Furthermore, Bologna signed an exclusive trade agreement with Ravenna for salt and grain, provoking a conflict with Venice. In 1258, the Venetians built a fortress on the mouth of the River Po to block grain transports to Bologna. Chronicles speak of subsequent dearth, food shortages, social unrest, and the Ghibelline families, collectively called the Lambertazzi, were accused of speculation in grain. Furthermore, we find a huge loan to the city from Florentine bankers and a loan forced on its own wealthy inhabitants. A third case study focuses on cultural implications. In 2000, when Richard Stothers connected the rise of the Flagellant movement in Italy in 1260 and it spread over half of Europe until 1262 to the 1259 event, as it was called then, this sounded quite absurd to historians, as the Flagellants themselves never referred to natural conditions, famine, dearth, as a reason for their actions. The little we know about their motives sounded purely religious. God's grace, peace, justice. But when I started to examine the movement's origins in Perugia, in the summer of 1260, a reaction to social tensions seemed most plausible. From 1255, a new popular government ruled Perugia in opposition to local magnates. In 1260, the government issued strict legislation against these magnates, claiming to preserve public order. But why was the situation so unstable? Perugia was a regular exporter of food in the first half of the 1250s, but already in 1256, we find in a volume of the protocols of the city council 21 discussions about dearth, grain confiscations, grain export bans, grain smuggle, tensions with other cities about food security. So we don't have any volumes for the years 57 to 59, but we know that Perugia had to interrupt a war against its neighbor Gubbio due to a lack of food for its army in 1258. In 1260, the once rich city was bankrupt. 1/4 of all villages around Perugia were forced to send their grain to the city, and most of these villages were owned by magnates. One argument in the strict laws of 1260 was that magnates speculated on grain to damage the city. So the harsh conflict which gave birth to the Flagellant movement was, as far as we can tell, fueled by the famine in Perugia in the years 56 to 58. Only in 1260, when people were no longer hungry, grain prices in Perugia had fallen to a mere 25% of what we find for 1258. An unprecedented religious movement could start in Perugia and spread across the continent, as far as Paris and Poland within 2 years. Now, these penitents have undoubtedly multiple intellectual sources, but I find it quite Yeah? No? Oh yeah, here it is. Okay. I find it quite striking that each of the Flagellant movement's reappearances up to the middle of the 14th century happened during or shortly after years of meteorological extremes. So if you're a climate historian of the Middle Ages, each of these years will ring a bell for ring a bell. Let me summarize my thoughts. The paper has tried to demonstrate that the phase of meteorological extreme events in the second half of the 1250s can't be simply synchronized with this Mars eruption. And yet, the volcano should be understood as a catalyst in an ongoing meteorological anomaly with a considerable societal impact, including failed harvests and dearth. Both the cases of Siena and Bologna explain why the economic downturn and the rise in grain prices did not result in widespread starvation in Italy. A sophisticated system of grain management and connection over long-distance trade routes combined with substantial wealth helped to avoid the worst. The close-up on Perugia showed that it is plausible that the weather-induced famine of the late 1250s contributed to social tensions that gave birth to the first, or at least the most prominent Flagellant movement of the late Middle Ages. So, thank you for your attention.
So why do people hit themselves on the back after volcanic eruptions?
Well, I just can say they started after one. Why? The direct connection is not visible. So well, what I can see from the sources, and we have to look to the city where it all started, that is Perugia, is, well, what we know from sources, I mean, they claim justice, peace, and God's grace. That's not very specific, and that's the same all along these 2 years. So, but to what tensions are they referring if they go for peace and justice? Well, the only tensions I really can find in Perugia in that time is this well, political tension closely connected to the food crisis. And a second question which I'm not ready to answer would be, but just as an idea, why is this movement so successful all over Europe? Are all people ready to join in this quite, even for the contemporaries, very strange behavior? So most cities in Italy open their gates to this movement. Some don't and say, these people are just crazy, we don't let them in. So, but there must have been there might have been a common experience. And maybe that's the Europe-wide food scarcity, famine in in the second half of the 1250s. That's my answer. I can't get more specific on that.
There's no apocalyptic dimensions to their movement at all.
Well, if you look to the sources from really contemporary sources from the 1260s, you don't find many detailed information. We have informations on the origins, but they come from the beginning of the 14th century. And yes, there's the broader religious background to this, of course. But it's difficult to use that as an argument. That's the way historical research has treated this movement, but they never had this close-up on Perugia, what exactly was happening in the city at the time. It's connected to a local cult of a saint. Yeah, but all this information comes from 30 to 40 years later. So that's difficult enough. And I just want to focus myself on the very situation, what's happening in that period, what might be the spark to ignite the movement. Afterwards, I think it has little to do with the famine and natural conditions at all. But why are people starting to do that in that very period? Yeah.
The severe winter of 939-940, or the Common Era, in Europe was argued to have been caused by a volcanic eruption. Studies of the past have identified Elkja, see it here, a volcanic fissure 17.5 kilometers long, belonging to the Katla volcanic system in southern Iceland, as being responsible for the extreme cold over Europe. So here you see Elkja and a more detailed map of the volcanic fissure. Today I would like to give a brief overview about what we know about the volcanic event, what can be said about causes, trigger effects, coping strategies, and finally what must remain uncertain. The region I am going to talk about is Western and Central Europe, and I am a historian, so I will focus on written sources. In 1917, geographer Karl Zappe dated the eruption between 930 to 950, and since that, studies from the natural sciences have dated the event to the second half of the 1930s. We have seen some datings today as well, ranging from 930 to 939. Written evidence from the 10th century was often used to calibrate the dating in the given studies. So examining documents of the time, the eruption detected in, for example, the ice core data, seems to have caused tremendous effects, as demonstrated by McCormick et al. In 2007 on a wider range, but they also focused on this special event I'm talking about today. So let's look at the written sources. The Irish documents report a severe winter in 939 and 941, and a flood in 939, and most striking, a red sun from one day to another in 933 and 939, although the annals are related to each other, the date is not exactly sure, especially in the terms of the annals of climate noise. So this observation, which may be interpreted as a consequence of volcanic aerosols in the atmosphere, has been argued to be an undoubted observation of the plume of the eruption of the volcano Elkja in Iceland. Well, it has to be said that the Elkja event is thought to be as huge as the Laki event of the 18th century. And in this case, we are looking for an event of significant impact. And the observation should have lasted for far more than 1.5 days to be convincing. I'm not sure if we can really apply an undoubted observation of the plume in that case. But however, something appeared unusual in the sky in 939 or 933, and the following winter was cold. This can also be mirrored by continental sources. Several documents of the time report a severe winter, an animal pestilence, and famines from 939 until 942. You can see here Widukind of Korva is a Saxon scribe, would be today Lower Saxony. We have the Annals Sangarensis, which is St. Gallen in Switzerland, Hermann of Reichenau, so southern Germany, and continuing, we have the Annals of Krakow, not quite contemporary, but drawing on contemporary sources. The Annales Labiensis, this would be present-day Belgium, and Photoart of Reims. They all mention an animal pestilence, a famine, and a hard winter. It was Widukind of Korva, the Saxon scribe, who seemed to deliver another reference to a volcanic eruption, and especially this part over here. Indeed, before the death of King Henry in 936, many prodigies occurred, such as the brightness of the sun outdoors in a cloudless sky appeared almost nil, but through the windows of houses it streamed indoors red as blood. And then, but a great flood did follow up on the appearance of the comets, and after the flood came a pestilence of cattle. So, while the report seems to be more evidence for phenomena that are related to the volcanic eruptions, especially this, the passage of the sky is really remarkable, we have to consider that this may be a literary instrument due to the fact that it was inserted. So it is unclear which date Widukind is referring to when he writes before of the death of the king. Is it 936, 935, 934? Maybe he's also transferring some observations from 941, and maybe he's just making up the miraculous story to entertain and emote the events he wants to describe. Linking celestial phenomena with unpleasant event is everything but exceptional in medieval historiography. We also have to bear in mind that the subsequent entry of the Red Sun in the Irish annals, in the Chronicon Scotorum, is a report of God's intervention after an occupation of the pagans. So in this case, we have also this combination of a bad omen that is predicting some bad things about to happen. So the Red Sun is remarkable, but there is definitely an uncertainty. So if we sum up this, the evidence from the written sources, there is plausibility, and the report of Widukind's observation is really remarkable, but information that would allow for a definite dating is missing. So if we can't go any further from the ice core data and combining it with the written evidence, let's have a look at other data available. If we look at the Old World Drought Atlas, we can observe extreme moisture over Central Europe in 939, rather wet conditions, 939, rather wet conditions in northern Italy and the western Balkan Peninsula, which is not my focus today. And then we have from 941, continuing until 945, we have an increase of summer dryness almost all over Europe, north of the Alps. So the Old World Drought Atlas doesn't give us the whole year. It gives us the summer months, June, July, and August. And the data may inform us about the circumstances of grain and harvest. It is possible that wet conditions led to a poor harvest in 939, since grain could not be stored in dry conditions and therefore started rotting. Less seeds could be saved for the next year. And then the harsh winter of 939-914 must have functioned as a trigger, diminishing the food supply for both man and animal. And the loss of cattle, especially draft animals, as mentioned in the texts, must have increased the shortfall in the subsequent years, since fewer animals were available for agricultural work. So in this case, the possible volcanic event did not produce the shortfall or the rise of mortality rates in the first place. It was rather the summer's moisture, the volcano's climate cooling effect, and the aftermath that unleashed the misery. So finally, if we think about cultural responses to natural impacts, this situation must have forced some coping strategies, or some reactions definitely, and it must have forced the ruling powers to take action. But interestingly, there is no contemporary papal or royal document, at least I don't know about one of them, of any administrative nature that explicitly formulates coping strategies. But there are earlier documents that might inform us about what people might have done to increase their resilience. The Capitulary of Herstal is a royal ordinance formulated by Charlemagne in 779. There it is. And what he basically formulates in this ordinance is ordinances concerning relief efforts that increased welfare by intensifying spiritual and economical aid, depending on the capacity of each community. The Capitulary covers masses, psalters, almsgiving, fasting, and hospitalization of hungry paupers until the beginning of the harvest season, meaning the day of John the Baptist, which is June 24th. So they were hoping for a better year. And while most of these ordinances have to be interpreted in a spiritual way, we have also admit that this is some pragmatic measurement. Almsgiving obviously is providing something to those in need. Fasting is a spiritual thought and salvation, or thought of spiritual salvation. But it's also a strategy of calorie reduction in an environment that offered limited calorie supply. And then finally, the hospitalization of hungry paupers also tries to increase the resilience of a community. Now, you might probably ask yourself why I am referring to a decree that was almost 160 years old back in the day. I'm doing that because we know about these ordinances from a collection of administrative decrees compiled during the first half of the 10th century in the region of Reims. And since some reports of the early 40s, 1940s, come from this region, it is likely that people acted according to the decrees, or at least found orientation in this old document. There is no information whether these decrees worked as an operational manual. However, if it was copied, we must take into account that it was also read and functioned as some sort of guidance in case of a similar tribulation as it appeared in the years 939 and following. So what I wanted to show you is much remains uncertain and perhaps always will be. But if we know about the uncertainties in both disciplines, we can calibrate our studies more accurately. And this leads to new questions and approaches to an understanding of the interrelationship between nature and culture. In this case, the summer wetness, the volcanic forcing, the means of agricultural production and their effects on food supply, and finally the coping strategies formulated in the Capitulary all together may answer questions concerning human reactions to stressors, in this case of a volcanic origin in pre-modern Europe. And therefore, we need to distinguish between topos and facts, as mentioned earlier by Thomas Wozniak. Thank you.
We published a paper 11 years ago now looking at the flow of the Nile River, and also found that 939 was the year when the flow went down caused by a reduction of precipitation in the source. So that really corresponds with your records.
Yeah.
The 934 date from ice cores before, I think, probably was a miscounting, and I think 939 really is the right year for that eruption.
Mm-hmm. Yeah. Yeah, I think the 939 really makes sense. What I just wanted to say is, if we are rechecking data that comes from natural sources, and we are rechecking it with historical documentation, we always have to keep in mind that it might also say something else. But in this case, the density of different kinds of information concerning the volcanic eruption is really striking, so that it's quite plausible that it appeared in 939. Yeah.
Good afternoon, everybody. Thank you for having me. It's a pleasure to be here and to talk about the Laki Fissure eruption with you today. I'm going to look at it from a perspective of environmental history. So, on the 8th of June 1783, it began. The Laki Fissure in Iceland's remotely located highlands came to life. This volcano, not a cone-shaped one, but a 27-kilometer-long fissure with around 140 craters, vents, and cones, erupted. From June 1783 to the following February. During these 8 months, the Laki Fissure produced around 15 cubic kilometers of lava, the largest amount of lava produced by any eruption in the last millennium. Here we can see a map of the Laki Fissure. It's right next to the Elkja fissure that we just heard about in Stephan's presentation, and the purple color indicates the lava flow produced by the Laki Fissure eruption. This gigantic lava flow did not kill anybody directly. However, the indirect consequences were catastrophic for Iceland. Until today, the consequential famine is remembered as Moduhadin, which translates as hardships of the mist. The gas, particularly the fluorine released during the eruption, covered and thus contaminated the fields and made grazing and farming impossible. The animal population and the main diet of the Icelandic people was decimated, and the Icelanders were starving. Diseases did the rest, and until 1785, about a fifth of Iceland's population, at the time around 10,000 out of 50,000 people, perished. However, as we've learned in 2010, when the Eyjafjallajökull eruption forced international air traffic to its knees, Iceland's eruptions and their consequences don't just stop at national borders. Just as in 2010, only to a larger extent, the Laki Fissure released 122 megatons of sulfur dioxide, among other gases, which were transported via the jet stream towards Europe and later dispersed over the northern hemisphere. In Europe, this ash and gas was visible and smellable as a dry fog, which is shown on the map you can see here. The fog was very peculiar. It was long-lasting and stayed on and off for 2 to 3 months, and it could not be dispersed by rain or storm. And it had a very odd sulfuric smell, which was noticed by the contemporaries. Unlike in the 2010 eruption, the world outside Iceland did not instantly learn about the Laki Fissure eruption. Instead, it took 3 months for the news of a volcanic eruption to travel to Europe via Copenhagen, which Denmark at the time was the colonial power in Iceland. By the time the news about the volcanic eruption reached Europe in early September, the dry fog was literally yesterday's news, and their contemporaries had already developed several theories as to the origin of this dry fog. The motivation behind this research paper was the aim to find out at what point in history was the connection between the dry fog and the Laki Fissure eruption understood. How did the contemporaries perceive and attempt to explain the dry fog and the other extraordinary phenomena until they established the connection between the Laki Fissure, to the Laki Fissure eruption? What led to this lifting of the fog of ignorance? To fully understand the reaction in Europe and outside of Iceland, it is important to keep in mind the other unusual meteorological and geophysical phenomena that the contemporaries witnessed themselves or read about in the newspapers at the time, which made them regard 1783 as an annus mirabilis, a year of awe. The other phenomena visible during the summer were a sequence of 5 strong earthquakes in Sicily and Calabria, as well as several aftershocks throughout the year, and earthquakes in France, Germany, and the Netherlands. The heat of the summer, blood-red sunsets and sunrises, a larger than usual number of thunderstorms, the appearance of 2 meteors over Europe, and the newly emerging island off the coast of Iceland. This list of unusual phenomena describes a unique sequence of different extremes. The natural sciences were not yet able to establish clear boundaries between them, so they were all brought together when trying to explain them. In 1783, Europe was strongly influenced by the Enlightenment, and in that spirit tried to explain the unusual natural phenomena of the time with reason. The dry fog and the phenomena were either believed to be caused by flooding and simply vapor as a result of the hot sun and heavy rains. Another theory involved electricity, either too much or too little of it. The most popular theory, however, was the idea of a subsurface revolution, which discharged sulfur from the Earth's interior and out through cracks in the Earth. Here we have a picture of what that looks like. And a revolution in this context does not describe a political upheaval, but an initiation of large and important change accompanied by unusual events. And a potential culprit was Hekla, which is another Icelandic volcano known in Europe at the time. It was known since medieval times as the Gate to Hell, and is depicted here in the middle as erupting. And this is as early as the 16th century. Benjamin Franklin is often attributed with figuring out the connection between the eruption and the dry fog. However, that's not really true. He was not the only one at the time. There were at least 3 other scientists who proposed a similar theory. And it's also overlooked that Benjamin Franklin at the same time suggested that a great burning ball flying by the Earth, and it's, probably what caused the dry fog. So it was just another speculation. At the time of the eruption and the years after 1783, we have several people who described the eruption in Iceland. And the first one that was published was by an Icelander called Holm, who lived in Copenhagen, and he received letters from people living in Iceland and published this hearsay. In 1785, another Icelander who traveled from Denmark to Iceland published a book. He did travel to the highlands, but he didn't travel far enough, and he also went there with a mindset of finding a cone-shaped volcano, which wasn't there in the first place, so he didn't find it. Another publication is by John Steingrimsson, who was a reverend in the parish that was most affected by the eruption, and he wrote it down as early as 1783, and thanks to his reports we know the exact dates of the eruption. This was published in 1788. Then there was an Icelander called Svein Pálsson. He was a naturalist, and he traveled through Iceland's highlands for 4 years, which is a very hard endeavor because you have to cross ice-cold rivers, and it's just physically very exhausting. And he actually discovered the fissure in 1794, and he accurately described the location and what it looked like. And he described it as a fissure. But due to unfortunate circumstances, his work was not published until 1945. So it didn't really make it into the contemporary discourse. However, he managed to give his manuscript to a Scottish missionary called Henderson, who traveled to Iceland in 1814, and he published this book in 1818, and he actually describes the Lucky Fissure as a fissure. He describes the location, but unfortunately, he doesn't seem to have any impact on the debate at all. Then we have a gap of about 60 years before the Lucky Fissure eruption sparked some interest again. The first one to publish about Laki was in 1879. It was Thorvaldur Thorvaldsson, an Icelander, and he also traveled the highlands afterwards. And in 1894, 100 years after Paulsen, he came to the Lucky Fissure. Another Norwegian who published on Laki was Amund Helland, who published parts of Paulsen's manuscript, and he also traveled to the fissure in 1881. And it's particularly interesting that Thorvaldsson and Helland published about the Laki Fissure eruption in 1879 and 1882, because in 1883 we have another very important event that significantly changed the debate. And I think you already know what I'm getting at. It's the Krakatau eruption of the 27th of August 1883, and the world had really changed in the last 100 years. Now there were telegraph networks, and they enabled, for example, the Europeans to receive news about this eruption almost instantly, and at the same time they could see those bizarre red skies over Europe or America, and they connected the dots. And the British Royal Society also created a Krakatau committee, and it was the committee's task to find all the facts about the eruption's impacts on the world, which published its findings in 1888 and also came to this conclusion. And only in retrospect, the dry fog and the Lucky Fissure eruption were understood too. It's important to also look at the history of geology in this context to understand why it took so long to connect the dots. From the establishment of geology as a discipline in the mid-18th century would be a long time before geologists would have a theory that explained continental movements, earthquakes, and volcanoes the way that plate tectonics does today. It is important to bear in mind that until the 1960s and 70s, the theory of plate tectonics was not yet accepted. So in the 18th century, geologists developed quite different ideas as to why earthquakes and volcanoes occurred. At a time when the discipline of geology was striving to identify laws behind phenomena that they observed in nature, volcanoes only played a very marginal role, as they would only erupt at odd, irregular times, which made it hard to impossible to find the laws behind the eruptions. And as Kenneth Taylor pointed out, volcanoes needed to become ordinary in order to be integrated into the thought world of early geology. To answer the research question of this paper, it can be concluded that the connection between the dry fog and the Lucky Fissure eruption had only fully been understood in the aftermath of the 1883 Krakatau eruption, when scientists as well as amateur weather observers noticed the global impacts of the Krakatau eruption. The same idea had been proposed by Paulsen and published by Henderson in 1818. Unfortunately, Henderson's publication did either not reach the right people or it reached them at the wrong time. Most likely it reached them too late. In 1818, the Lucky Fissure eruption was already a 35-year-old event. And the fact that Henderson groundbreakingly described the Lucky Fissure as a fissure did not seem to have had any impact at all. So all this time, from 1818 onward, there was a book that described the Lucky Fissure as it was, but it was essentially ignored. Which brings us to the definition of ignorance in this context. Initially, the ignorance was understood as the missing link between the eruption and the natural phenomena it caused in Europe. The Icelandic people had been very aware of the eruption from the beginning, but later it seems ignorance cannot be described as oblivious behavior, but as a deliberate act to not take certain information into account. What finally lifted the fog of ignorance was the almost instant communication between different parts of the globe via telegraphy. The Krakatau media presence, thanks to the establishment of telegraph networks, made it possible to understand that even a distant tropical volcanic eruption could cause bizarre red skies and sunsets on the other side of the world. Only in retrospect could the dry fogs during the summer of 1783 be brought together with the Lucky Fissure eruption. Thank you.
I was wondering how the relation is between religious and
whatever scientific explanation at the time. So do they mix, as other historians have stated, for the early 1750s on meteors, earthquakes? And second question, do you use homilies or preaching texts as a source, or just focus on the newspapers? Yeah.
Okay, so to answer your first question, I mean, religion still plays a role, like even when the scientists answer or argue, they would still integrate God. Religion doesn't play a role in the foreground anymore, but God is still there in their arguments. And to answer your second question, I looked at newspapers, and I also looked at scientific publications from around 1783, as well as the travelogues that were published by the Icelanders and the Norwegians and the Scottish and so on.
Thanks very much. This is work done with my postdoc, Joanna Slowinska. I'm going to begin with an advertisement. I'm an editor of Reviews of Geophysics, and so if you have a review in you, please talk to me. No page charges as long as you want, high impact factor. We looked at the question of did volcanic eruptions produce a little ice age, and this is starting with the work by Giff Miller and Aslaug Gersdottir and their postdoc. We took advantage of the last millennium ensemble of 28,000-year simulations done at NCAR by Betty Otto-Bliesner and her group, and they did one long control run and then ensemble members with different types of forcing, just volcanic, just solar irradiance, the other causes, and 10 with all the forcings together. And this is based on a paper we have in review now at Journal of Climate. First of all, we looked at the impact by compositing the 10 largest volcanic eruptions that occurred during this period. And the top row is, on the left is all forcings, and on the right is volcanic forcing only. And the top row is the winter, Northern Hemisphere winter of the year before the eruption. And the middle row is the year after the eruption, first winter after the eruption, the second winter. And so what you can see is not much happening, and then you have this characteristic winter warming over Eurasia in both cases, and the next year you have an El Nino also, and the winter warming has gone away. Another thing to notice is that just by chance, in the 5 ensemble members with volcanic eruptions, it was warm in the winter before, so there was less sea ice there, and that affects the response. In the all forcings, there was nothing particularly anomalous in the year before. We also looked at the summer, and we saw what you would expect, which is a reduction. This is the year of the eruption, a reduction of precipitation over Eurasia, and this is related to what Francis talked about before, about the possible impacts on Chinese dynasties because of an effect on the crops. The forcing that went in, Gavin is the first author of this, shows the different types of forcing. These are the volcanic forcings, and the gray shading is the different types of solar forcing. And just by chance, after Samalas, there was a slight reduction of the solar constant in the forcing. And after the second biggest eruption of Kauai, there was also a reduction. So it looks like it's a little bit hard to separate. Both of these would produce cooling. If you look at however, the forcing that actually went in, the volcanic forcing had a very large reduction. This is in watts per square meter. And the solar forcing was very minimal. So if you add them together, the volcanic forcing dominates. This is the result in terms of the area of Arctic sea ice, plotted on the left. And the first line is the volcanic forcing. The second is the AMOC, the Atlantic current. And you can see that in years after the eruption, the AMOC got a little bit stronger. That is, the cooling in the North Atlantic produced a stronger circulation. But then it went into a mode where it was weaker, and after Kauai, the same thing. Now, the question is this the little ice age? There was a shift after Samalas to climate with more sea ice that persisted for the entire length of the simulation. And if you continue this with volcanic eruption, with natural forcing after this, you get a reduction with global warming. And you get this in the case with all the forcing. Each of the colored lines is one of the ensemble members. The black is the average. If you look just at the volcanic forcing, there's a hint of that, but it's not as strong as with all forcing. So the question is, why is that? Do you actually need the solar forcing by itself doesn't really produce anything, but is the combination of all the forcings, including solar and volcanic, what produces the little ice age or not? So first of all, we looked into the AMOC. This is a correlation of the northward heat flux in the Atlantic as a function of latitude with the area of the sea ice. And so in the high latitudes, there's a strong negative correlation. That is, if there's stronger heat flux, there's less sea ice. And so if the volcano produces a stronger AMOC and stronger heat flux, you would think it would actually go in the opposite direction, that there would be not an ice age, but it would melt the ice. Still, you got more ice. So why is that? If you look at the AMOC, and there's also a question about what is a volcanic response to AMOC. Different models get different responses. Some produce more, stronger, some produce less. This model has an AMOC natural variability period of about 15 years. And so this is for the 5 runs with volcanic forcing and the 10 eruptions. So there's 50 lines here. And before the eruption, AMOC can be in any phase, but afterwards there's a tendency for a stronger AMOC. So in the short term, the volcanic eruption would produce a little bit more heat flux. If you separate the volcanic eruptions by their size, this is the AMOC anomaly at the initial condition in terms of the 35 north maximum flow of heat. And there's no preference, but 8 years after, which is this axis, for the largest eruptions, it's stronger. And as you go to the smaller eruptions, there's basically nothing. And this line shows that it sort of switches phase over 8 years. But for the strong eruptions, it's positive. But this is the Arctic sea ice anomaly for the forcing with all eruptions, with volcanic eruptions, and the 4 with solar eruptions. This is the area, this is the years after the eruption for Samalas and for Huayna Patina, 2 of the largest eruptions. And you can see that just by chance, and you get actually more sea ice. So even though the AMOC is a little bit stronger, the radiative effects dominate, and that's what produces the little ice age. Even though the AMOC for a few years is stronger, the longer time response is because of the cooling. And just by chance, the volcanic forcing, the Arctic sea ice for the volcanic forcing cases started off with less sea ice, as I showed you in one of the first slides. And so even though you get more sea ice, it doesn't get quite as much as for the all forcing. And we think that's because randomly the initial conditions started at a little bit colder climate. This was a warmer climate with less sea ice, just by chance for this eruption and for this eruption, and therefore you get less of a response. For the solar cases, there was just happened to be cold for this with more sea ice, but there's not much of a response at all. So what we're doing now is we're doing simulations starting with exactly the same initial conditions with the same model for a number of ensemble members with just volcanic forcing, just solar, and the combination to see whether volcanoes really are the dominant case. Maybe the sun helps a lot, but the way this experiment was done, just by chance, you really can't answer the question, did volcanoes cause the little ice age by themselves, because they just happened to start with a warmer climate. So the conclusions are, in the last millennium ensemble, the volcanic eruptions are followed by a decadal scale positive response of the AMOC, but centennial scale enhancement of sea ice. And you need the large volcanic eruptions to explain the origin and the duration of the Little Ice Age-like perturbations. And prolonged reductions in solar radiance seem to maybe enhance the effect, but further experiments are needed to figure out what the net effect is. And we hope that these experiments will also be done with other climate models. Thanks.
Alan, you didn't say where this sea ice is extending. If you have, is this end of summer sea ice, September sea ice, and is it in the North Atlantic? Is it on the coast of Greenland?
It's the extent of summer sea ice, so it's the end of the summer, September.
But where is the expansion of sea ice over the centennial scale? Where do you see it? Is it in the Bering Sea, or where is it?
No, it's in the eastern side. I didn't show them. We have maps, but I didn't have time to show them.
In the
but the mechanism where the transport of energy from the North Atlantic into the Arctic is blocked by this different mode of circulation is supported by these results. The original runs that were done only had 4 ensemble members, and 2 gave it and 2 didn't, so we took advantage of the much larger number of ensemble members. But yes, that's where it is. It's the transport of heat from the whatever the sea is called near Norway into the Arctic.
I think it's called the Norwegian Sea.
Well, there's a fancier name for the place closer to the Arctic, but yeah.
So the heat transport connected with the AMOC, as you see that mainly at some latitude like 30 north. If you look at 60 north, what's really important for what go to the Arctic, it's more related to the gyre transport. And we have seen in models at least that even like for the 20th century, when we see a decline of the MOC, there's an increase of heat transport to the Nordic seas by a stronger gyre circulation. So it would be worth probably to look into that aspect as well.
Yeah, so it's the gyre circulation north of that that's more important than the AMOC, that's right.
We had a longer discussion in the IPCC about the starting date of the Little Ice Age. It's clear that the second millennium is cooler, and also due to orbital forcing, but the discussion was about when it started, because someone said it started after the first strong volcanic event, 1257. But another part of the group was telling we had a dampened reaction in the Southern Ocean and a later beginning of cooler temperature in the Southern Ocean. So they voted for a later time, 1400, and that was then printed in the 5 AR. I voted for the first volcanic event as a beginning of the Little Ice Age. Even we know that the Little Ice Age started at different time in different regions.
Well, you can go back to Giff Miller's work in Baffin Island, where he found that this expanse of the glacier was after the first eruption. There was another kick, of course, from Kauai, and another kick from Parker and Huaynaputina, but certainly I think it started with this set of eruptions at the end of the 13th century. The original definition of the Little Ice Age was very Eurocentric. It's what they saw in Europe, but now that we have more data, it looks like it really started before that.